Welcome to the deep dive. Today, we're getting straight into something absolutely critical for modern manufacturing: quality control.
Right, that whole idea of zero defect products.
Exactly, especially now with Industry 4.0. I mean, Think about it. How do you make sure every single part, every single item coming off a line is perfect?
Yeah, and when products are constantly changing or getting customized, it's a huge challenge, high stakes.
It really is. And that's what we're diving into today. We're looking at this fascinating new study. It explores how quantum computing is actually stepping up to solve this problem.
Specifically, optimizing the paths robots take for quality inspection.
Precisely, the efficiency of movement.
Yeah, the source we're looking at today is a study called Quantum-Assisted Automatic Path Planning for Robotic Quality Inspection in Industry 4.0.
Okay.
It's by Eneko Asaba and a team from Technalia, the University of the Basque Country, and the University of Calabria. So our mission for you listening is to really get how these hybrid quantum classical algorithms are making industrial robots smarter.
And faster. Right, more efficient.
Dramatically faster and more efficient, making sure product quality is top-notch.
So you mentioned zero defect. Factories are using more machine vision, more robotics for this kind of flexible quality control.
They have to.
But how do they know where to go? I mean, take a complex part like a car door or, even a toy bear.
Yeah.
How does the robot know the route to inspect every little bit?
Well, the standard approach for a while now has been automatically generating these paths from the product's CAD file, the computer-aided design file.
Okay, but digital blueprint.
Exactly. But the key thing is the final trajectory, the actual sequence of movements to hit all the inspection points. That needs to be figured out by an optimization algorithm.
It needs a smart plan.
A very smart plan. You can't just have it wander around.
So finding the most efficient way to visit all these points. That sounds familiar. Is this like the Traveling Salesman Problem?
It is, basically. Oh. The researchers modeled this as a 3D version of the classic TSP, finding the shortest route to visit a bunch of cities.
Right. But I imagine this industrial version has some extra wrinkles.
Oh, definitely. Big ones. First, like you said, it's 3D space, not a flat map. Second, it uses what's called an incomplete graph.
Meaning?
Meaning not every inspection point can be reached directly from every other point. Think obstacles on the factory floor, machinery, the robot's own reach limitations.
Real-world constraints. Makes sense.
Exactly. And third, it often needs open routes. The robot doesn't always have to end up back where it started. And these complexities, that's where the standard classical optimization methods can really, start to bog down, especially when you have lots and lots of inspection points.
Which brings us to the quantum part. This is where it gets really interesting because we're seeing quantum computing move beyond just theory.
Right, into practical applications.
Hybrid approaches.
Hybrid quantum classical methods. So how did the study use them? What did they look at?
They used D-Wave's hybrid solver service.
Yes.
Specifically, they focused on two solvers. One called CQM-Hybrid, that's constrained quadratic model.
And another called NL-Hybrid, the nonlinear program hybrid solver. And what they found, after a lot of testing, was that the NL-Hybrid consistently gave better results for this specific type of problem.
NL-Hybrid. And how does that one work? You said it's hybrid.
Yeah, it's pretty clever. It works in two phases. First, there's a classical heuristic module that uses regular computing power to explore the possible solutions, sort of map out the territory.
Okay, the classical part does the initial legwork.
Right. But then there's the quantum module. This part sends queries to D-Wave's actual quantum processor, their QPU.
The Advantage system, I think they mentioned.
Advantage system 6.4, yeah. And these quantum queries aren't just trying every possibility. They intelligently guide the classical part.
Guide it? How?
They help point it towards more promising areas of the solution space, or they help refine the solutions the classical part has already found. So the quantum element is kind of like a smart navigator.
That's fascinating. It's not just raw power, it's guidance.
Exactly. That's the secret sauce, you could say.
So what makes this NL-Hybrid better suited for this TSP variant than, say, the CQM one or other methods?
It seems to be because its decision variables, the way it frames the problem mathematically, can directly represent the order of the inspection points, the permutation of nodes.
So it's naturally good at sequencing tasks.
Precisely. It kind of thinks in terms of ordering things, which simplifies the math for this specific problem, makes it a really good fit.
Okay, makes sense. Now, the proof is in the pudding, right? They tested this on real industrial cases.
They did. 5 real-world examples. A car door, a car rear bumper, a toy bear, a model airplane, and a half-sphere shape.
quite a range. And how do they define the inspection points for something like, say, the car door? Are we talking every tiny detail?
It gets pretty granular. They segmented the surfaces based on things like area and how much the direction the surface faces changes.
So quite detailed.
Very. And the costs in the optimization weren't abstract. They were based on the robot's actual expected movement time and energy use between those points.
So really grounded in practical factory operations.
Absolutely.
Yeah.
Designed for real-world use.
And to see how well this quantum-assisted approach performed, they needed benchmarks. What did they compare it against?
Right. They used two main classical benchmarks. First, Google OR-Tools, which is a well-respected classical solver library.
Okay.
And second, GUROBI. GUROBI is a really powerful, exact classical solver. It's often used as the gold standard in these kinds of comparisons because, given enough time, it can find the mathematically proven best solution.
The optimal one.
The optimal one. In fact, they used GUROBI's results to calculate something called the approximation ratio, or AR. That measures how close the other methods got to GUROBI's perfect solution quality.
Got it. So AR for quality and runtime for speed.
Those are the key metrics, yes.
Okay, drum roll time. What did the results show? This is where it gets really interesting.
It really does. So, first, comparing the two hybrid solvers. NL-Hybrid clearly beats CQM-Hybrid. Better solution quality, faster computation time, hands down.
Okay, so NL-Hybrid was the better quantum hybrid choice. How did it stack up against the classical guys?
It also outperformed Google OR-Tools. Again, better quality and faster.
Impressive. But the big comparison is against GUROBI, the optimal solver.
That's the crucial one. And here's the headline. NL-Hybrid didn't always find the absolute best solution like GUROBI did. GUROBI is designed for that. But it offered competitive solution quality.
Close enough for practical purposes.
Very often, yes. And it did it with dramatically reduced computation time.
Dramatically reduced. That's the key phrase, isn't it?
It absolutely is. That's the game changer here. It's not just about being slightly faster. It's about hitting a sweet spot that's actually viable for industry.
Where waiting hours just isn't an option.
Exactly. Let me give you the numbers for the H-Sphere instance. That was the biggest one. 194 points, nearly 400 connections.
Okay.
NL-Hybrid found its solution, on average, in just 5.4 seconds.
5 seconds, wow.
Compare that to Google OR-Tools, which took 13.5 seconds. Still okay, but slower. Now look at GUROBI. To find the absolute perfect, optimal solution, it took, wait for it, 68,400 seconds.
68,000, that's carry the one. Over 19 hours.
19 hours versus 5 seconds for a competitive solution from NL-Hybrid.
That's not just an improvement, that's a fundamental shift. Imagine waiting 19 hours versus 5 seconds on a busy production line.
It completely changes the calculus for real-time quality control. You don't have massive delays waiting for an inspection plan, huge time and cost savings potential.
Incredible. That speed difference is just mind-blowing. And I think you mentioned they even have visuals of this.
Yeah, the paper includes a figure showing the model aircraft instance and the path generated by NL-Hybrid. It helps visualize what these optimized routes actually look like.
Really brings it home. So wrapping this up, what's the big takeaway for our listeners?
I think this study is a really powerful, tangible example. It shows quantum computing isn't just, far off theoretical stuff anymore.
Right. It's actually solving complex real-world industrial problems today on the factory floor.
Exactly. It's providing practical value now through these hybrid approaches.
And the implications are pretty broad, aren't they?
Huge. This isn't just about making inspection faster. It's pushing the limits of automation itself. Achieving levels of efficiency, reliability in manufacturing, things we couldn't really imagine before with purely classical methods.
It really makes you wonder, how will breakthroughs like this keep reshaping industry? What comes next?
That's the big question, isn't it? How much further can we optimize? Higher quality products, incredibly efficient production.
So here's a final thought to leave you with. Imagine a future where pretty much every product you buy your car, electronics, even kids' toys, has been checked over, perfected, not just by human eyes, but by robots. Robots guided by the speed and intelligence of quantum computation.
It feels like we're just scratching the surface.
Definitely feels that way. This is just the beginning.